Have you ever wondered what invisible forces orchestrate the massive, continuous movement of water across our entire planet? It is truly a marvel. The sheer scale of ocean currents, tirelessly circulating, has profound effects on our weather and ecosystems. At their heart, temperature gradients contribute significantly to ocean current drivers by creating differences in water density, which then power some of the most substantial currents on Earth, known as thermohaline circulation. This process is a cornerstone of oceanography, influencing everything from regional climates to marine biodiversity. Imagine the ocean as a giant liquid conveyor belt, operating on subtle but powerful physical principles. Colder water is naturally denser and heavier than warmer water. Similarly, saltier water is denser than less salty water. When these two fundamental factors, temperature and salinity, combine, they create powerful density differences within the ocean. Consider the polar regions, for instance. Here, surface water becomes exceptionally cold. As sea ice begins to form in these frigid conditions, a fascinating process occurs. The ice preferentially expels salt, leaving behind the remaining seawater even saltier and thus significantly denser. This exceptionally dense, cold, and salty water then sinks. It descends into the deep ocean basins, often to depths of thousands of feet. Once it sinks, it doesn't just stop there. Instead, it embarks on a remarkably slow but persistent journey, moving across the vast ocean floors. This deep, cold current effectively draws or pulls warmer, less dense surface water from more equatorial regions towards the poles to replace the sinking water. This continuous cycle of sinking, horizontal movement, and subsequent rising of water, meticulously driven by these small but crucial variations in temperature and salinity, forms a colossal, interconnected global ocean circulation pattern. This circulation pattern is not confined to one ocean but links them all, creating a truly global system. Understanding these density-driven processes is incredibly valuable for scientists and climate researchers. It enables them to construct sophisticated and accurate climate models that help predict future environmental conditions. By meticulously monitoring ocean temperatures, salinity levels, and the precise speed and direction of these currents, often using advanced instruments like the globally deployed network of Argo floats and satellite altimeters, researchers can accurately map these crucial gradients. This comprehensive data is vital. It helps us not only predict long-term shifts in global climate patterns, but also anticipate more immediate phenomena like the intensity of hurricanes, and even understand complex biological behaviors, such as the migration patterns of various fish species. It is akin to having an incredibly detailed, three-dimensional weather map, specifically designed for the entire ocean system, offering insights for beyond what we could see at the surface. This grand oceanic system, often formally referred to as the global conveyor belt, or more scientifically as meridional overturning circulation, is for more than just a mechanism for moving vast quantities of water around the globe. It acts as a critical, fundamental regulator of Earth's climate system. Without its continuous operation, the vital redistribution of heat from the sun-warmed equatorial regions towards the colder polar areas would not occur effectively. This would inevitably lead to far more extreme regional temperatures and profound changes in weather patterns worldwide. Moreover, this circulation plays an indispensable role in the distribution of essential nutrients. It brings nutrient-rich waters from the deep ocean, where organic matter decomposes, back up to the surface. These upwelling nutrients are absolutely crucial for fueling the primary production of marine ecosystems, forming the base of the food web where sunlight can support flourishing life. This complex and beautiful interplay of temperature, salinity, and density is truly a fundamental principle of physical oceanography, showcasing the delicate balance of our planet. Grasping how these differences in temperature and salinity drive such immense and influential ocean currents empowers all of us to better comprehend our planet's intricate climate system, enhance our ability to predict future environmental changes, and deepen our appreciation for the delicate and interconnected processes that sustain all marine life. It powerfully illustrates how seemingly small, localized differences in water properties can collectively create global impacts that shape our world.